You know, in some places of the world, engineers have built things directly over active fault lines. These buildings are designed to bend, sway, and survive when the ground gives way. So for today's video, I'm going to take a look at 15 skyscrapers that were built in earthquake zones. Starting with number 15, Taipei 101 in Taiwan. At 508 meters tall, Taipei 101 was the tallest building in the world when it opened in 2004, and it does remain one of the most remarkable feats of earthquake engineering ever built. It's located less than 200 kilometers away from the boundary of two tectonic plates. The core of this building consists of high-strength concrete walls with reinforced steel, forming a rigid spine. Around it, 36 columns of steel and concrete provide additional support. The structure tapers as it rises, and it kind of resembles a bamboo stalk, not just for symbolism, but to help distribute the weight and reduce wind resistance. The key to its stability lies in the tuned mass damper. This is one of the largest ever built. It's suspended between the 87th and 92nd floors. This 660-ton steel sphere acts like a giant pendulum. When the building sways during an earthquake, the damper moves in the opposite direction, countering the motion and reducing vibrations by up to 40%. It is visible to people, and it shows how technology and tradition can coexist in this design. The foundation extends 80 meters down into the ground, and that's supported by 380 concrete pillars that are drilled into the bedrock. Engineers used a system of flexible joints and high-performance steel down here to absorb shock without snapping, which is a principle known as ductility. But Taipei 101 has already proven its strength multiple times. In 2002, when it was still under construction, a 6.8 quake struck the region. Although several cranes on top of the tower were damaged, the structure itself suffered no significant harm. Taipei 101 is now studied worldwide as a benchmark for high-rise safety in seismic zones. It is possible to build a taller, safer structure even in one of the world's most active tectonic regions. And today, it's not only a symbol of Taiwan's economic strength, but also of its engineers' mastery. Number 14, the Salesforce Tower in San Francisco. The Salesforce Tower, it dominates the San Francisco skyline at 326 meters tall. This is the tallest building in the city, and the second tallest west of the Mississippi. Its location, though, is one of the most seismically active in the world. San Francisco sits near the San Andreas and Hayward faults, which are both capable of producing major quakes. The building, completed in 2018, was designed by the firm Pelly Clark Pelly Architects with structural engineering by Magnus & Klemenchik Associates. This building uses a steel frame encased in reinforced concrete, which is a hybrid system that combines flexibility of steel with the strength of concrete. The structure sits on 42 massive piles that extend about 90 meters down into the bedrock, and these piles are anchored deep enough to bypass the city's unstable fill and clay layers, which does tend to amplify seismic waves. The design of it ensures that the building can sway up to nearly a meter at the top without causing any damage to its frame or interior systems. This flexibility does prevent brittle failure, which is a major cause of building collapse during large seismic events. During construction, engineers ran computer simulations using ground motion data from the previous California earthquakes, including the 1989 Loma Prieta and 1906 San Francisco quakes. These tests confirmed that the Salesforce Tower could withstand an event similar in magnitude without any structural collapse. Unlike some other San Francisco towers like the nearby Millennium Tower, which has suffered foundation settlement, Salesforce Tower has no measurable tilting or sinking since completion. The building's slightly tapered shape and aerodynamic design also help it reduce lateral wind load. The tower, of course, is equipped with state-of-the-art monitoring systems that record seismic activity and structural response in real time, and data from these sensors are shared with engineering institutions across California, helping to refine earthquake design standards for future projects. Number 13, the Torre Mayor, Mexico. The Torre Mayor is one of the tallest and most earthquake-resistant buildings in Latin America, and it's in one of the world's most dangerous seismic zones. It's located in Mexico City. This 225-meter tower rises 55 stories. It's right in the heart of a city built on the soft sediment of an ancient lake bed. This type of soil does amplify seismic waves, making even distant quakes feel much stronger. Completed in 2003, hidden within this structure are 98 giant shock absorbers known as dampers that act as mechanical cushions. During an earthquake, these devices absorb and dissipate the energy transmitted through the ground, preventing it from traveling up the entire structure. Essentially, they allow the building to move slightly and flex rather than resist the motion entirely. That's a principle known as controlled deformation. The building is divided vertically into 5 segments. Each is designed to respond independently to seismic motion, which will reduce the stress between the floors. This kind of modular design ensures that no single section bears the full force of an earthquake. The design was put to a test almost immediately after construction in January 2003, while the finishing touches were still underway. A 7.6 magnitude earthquake struck the state of Colima, roughly 500 kilometers away. The tower swayed visibly but suffered no damage. It's a powerful validation of its engineering. Later, during the 2017 Puebla earthquake, magnitude 7.1, the building again performed flawlessly. Its construction set a new benchmark for earthquake-resistant design in Latin America, and it influenced subsequent projects in Chile, Peru, and Colombia. This building is proof that skyscrapers can stand tall in even one of the most challenging environments on the planet. Number 12. The Tokyo Skytree in Japan. Tokyo Skytree is not only Japan's tallest structure at 634 meters, it's also one of the world's most earthquake-resistant towers. Completed in 2012, it dominates the skyline of Tokyo, a city located on one of the planet's most active fault networks. Earthquakes are a daily possibility here, and major events like the 2011 Tohoku quake show the need for durable structures. The design draws inspiration from traditional Japanese architecture, particularly the ancient pagoda. Pagodas have survived centuries of quakes because their central wooden columns allow each floor to move independently, which dissipates the seismic energy. Engineers adopted that principle for the Skytree, replacing the wooden column with a central reinforced concrete shaft surrounded by steel framework. During a quake, the outer steel frame and inner concrete core move at slightly different rates, with the dampers absorbing up to 50% of the vibration energy. At the foundation, the Skytree is anchored by a 50-meter deep pile system extending into the clay-heavy soil here. The base spreads the load evenly and prevents uneven settlement during ground shaking. The tower was completed just 1 year after the devastating 2011 quake, and its seismic systems were tested in simulations replicating that event. Engineers confirmed that it could withstand ground motions exceeding those of the 1923 Great Kanto earthquake, an event that leveled much of Tokyo. In smaller quakes since then, though, including the 2021 Fukushima earthquake, sensors have recorded only minor oscillations well within design tolerances. More than just a broadcasting tower or a tourist attraction, Skytree is a symbol of Tokyo. It's a reminder that even in one of the world's most earthquake-prone cities, human ingenuity can rise safely above the shifting Earth. Number 11. The Transamerica Pyramid in San Francisco. Hey, we're back in San Francisco. Few skyscrapers are as recognizable as the Transamerica Pyramid, a defining feature of San Francisco's skyline since its completion in 1972. At 260 meters, or about 850 feet, it was once the tallest building on the U.S. West Coast. But what truly makes it extraordinary is how it has endured decades of seismic activity. The pyramid shape wasn't chosen purely for aesthetics. The tapered profile dramatically reduces the building's weight towards the top, lowering the center of gravity and minimizing any sway during a quake. Architects designed the building to handle the horizontal and vertical shaking using a combination of flexibility and strength, the same principle seen in modern skyscrapers decades later. The foundation extends 15 meters, about 50 feet below ground, into the bedrock. It rests on a massive concrete slab nearly 3 meters thick, reinforced with over 400 steel rods. The building's steel and concrete frame is braced by a central core and a unique system of diagonal trusses that act sort of like shock absorbers during a quake. They connect to the apex, distributing seismic forces evenly. When the 1989 Loma Prieta quake struck, a magnitude 6.9 event, it caused widespread damage across the Bay Area. The Transamerica Pyramid swayed more than a foot side to side but suffered no structural damage. The elevators automatically shut down while occupants felt strong shaking. The building did remain completely stable. After inspections, it was one of the few skyscrapers in downtown San Francisco that didn't require repairs. Data from the sensors in the building have been used by the USGS to improve earthquake safety codes for other buildings. The pyramid's performance during Loma Prieta became a case study in earthquake engineering, and it's cited frequently in textbooks and design manuals. More than 50 years after it was completed, the Transamerica Pyramid is a model of stability in a city defined by seismic risk, an elegant demonstration of how form and function can work hand in hand to defy the forces of nature. Number 10. Abeno Harukas, Osaka. Abeno Harukas rises 300 meters or 984 feet above the city of Osaka. It's located in one of the most seismically active nations on Earth. Completed in 2014, it's right above one of the busiest railway hubs in western Japan, where the ground beneath is constantly vibrating from traffic, trains, and occasional tremors. The building's name, Harukas, means to brighten or clear up in Japanese, and the structure reflects that spirit. But beneath the elegant exterior is one of the most sophisticated seismic systems ever implemented into a Japanese high-rise. The structural system consists of a steel and reinforced concrete frame supported by a hybrid dampening mechanism. At its core are giant vibration control devices, 16 massive oil dampers, and 10 steel braces filled with viscous fluid that absorbs seismic energy. These dampers convert the motion into heat, which drastically reduces the building's sway during any quakes. It incorporates a series of outrigger trusses that are connected to the central core to the perimeter columns, and they distribute stress evenly across the structure. The whole building's divided into multiple sections, each designed to move independently. The lower levels contain the department store, while offices occupy the middle floors and a hotel fills the upper portion. This kind of segmentation helps isolate any movement, which is an important safety measure when housing different types of occupants. Engineers had to drive 80 deep piles into Osaka's dense clay, anchoring the structure into more stable strata. The foundation does minimize the effects of any soil amplification, which is a major concern in Japan's coastal cities where soft ground can magnify the seismic waves. The entire system was tested in simulations which replicated earthquakes up to magnitude 8.0, including ground motion data from the 1995 Kobe earthquake. During the 2018 Osaka quake, the magnitude 6.1, which shook the city with intense ground motion, this building performed flawlessly. It swayed gently as designed, and interior damage was negligible. Sensors placed throughout the tower recorded data for further analysis, helping refine future skyscrapers in Japan. This building shows that strength and grace can coexist. Standing above one of Japan's most populated and geologically active regions, it's proof that the country's long experience with quakes has evolved into an art form of structural design. It's one where beauty, science, and safety meet at 300 meters above the ground. Number 9. The Petronas Twin Towers of Malaysia. Although Malaysia is not directly on top of a major fault line, Kuala Lumpur's Petronas Twin Towers are designed with the full understanding that seismic activity from nearby regions, particularly Sumatra, Indonesia, could pose a serious threat. When the towers were completed in 1998, they were the tallest buildings in the world at 452 meters, 1,483 feet. Given their height and design, engineers faced a challenge of ensuring that distant earthquakes wouldn't cause any structural instability. Each tower features a high-strength reinforced concrete core surrounded by a perimeter of super columns made of concrete and steel. Concrete was chosen instead of an all-steel frame because it provides greater stiffness and damping, an advantage in both wind and seismic conditions. This reinforced concrete's among the strongest ever used in a skyscraper, up to 80 megapascals in compressive strength, allowing the towers to remain rigid even during regional seismic tremors. At the foundation, engineers drove 104 concrete piles up to 120 meters deep into their limestone bedrock. The base mat alone is 4.5 meters thick, and it contains more than 13,000 cubic meters of high-strength concrete. Now, while Kuala Lumpur doesn't experience quakes like the magnitude seen in Japan or Chile, the towers were designed to withstand lateral forces comparable to those from a moderate to strong seismic event. Engineers simulated the effects of earthquakes originating in the Sumatran fault zone, which is about 400 kilometers away, and these simulations confirmed that the tower could endure distant tremors without any damage. Oh, and that famous sky bridge connecting the two towers at the 41st and 42nd floors also has built-in safety functions. Rather than being rigidly attached to both towers, it's designed to slide and flex, accommodating the slight movements of each building independently during wind or seismic activity. During real seismic events, though, including the 2004 Indian Ocean earthquake and tsunami, minor tremors were felt in Kuala Lumpur, and sensors recorded small vibrations in the towers. They performed exactly as designed, swaying gently but returning to equilibrium without any structural or cosmetic damage. Number 8. The Lotte World Tower in South Korea. At 555 meters, that's 1,819 feet, Seoul's Lotte World Tower is one of the tallest buildings in Asia and a landmark of engineering. It's in a region not known for constant quakes, but close enough to the boundaries of the Eurasian and Philippine sea plates to experience tremors, like the 2016 quake and the 2017 Pohang earthquake, which both rattled South Korea. Because of that, seismic safety was a central concern. Completed in 2017, the tower was designed by Kohn Peterson Fox Associates with structural engineering by Leslie E. Robertson Associates. They're a firm that's renowned for its expertise in tall buildings. The building's shape, tapering as it rises, not just aesthetic, it's functional, reducing wind loads and distributing stress. The structure uses a composite system of steel and reinforced concrete. The core, which has elevators and utilities, is made of ultra-high-strength concrete up to a meter thick, while the perimeter frame includes massive steel outriggers that connect the core to exterior columns. These outriggers act as stiff arms, spreading the forces evenly during ground motion and preventing torsional or twisting movement. In total, the building has more than 200,000 cubic meters of reinforced concrete and 30,000 tons of steel. Engineers installed 172 concrete piles extending up to 110 meters deep into the bedrock to anchor this thing, and that ensures stability even in the event of a magnitude 7.0 quake, a level far greater than any quake ever recorded on the Korean peninsula. The designers included a 1,000-ton tuned mass damper near the top. That's one of the largest in the world, designed to counteract wind and seismic oscillations. When the building moves, the damper swings in the opposite direction and absorbs the energy and restores balance. The seismic capabilities of the tower were tested during construction using large-scale shaking simulations, and its design does comply with standards used in Japan and the United States, two of the world's strictest codes. During the 2016 and 2017 quakes, which were felt in Seoul, monitoring instruments recorded minor vibrations, all within predicted limits. It was built to endure nature's tremors and the forces of time. It rises not just up as a symbol of Seoul's progress, but as proof of human ingenuity in the face of uncertainty. Moving on to number 7, the Jin Mao Tower in China. Standing at 420 meters, or about 1,380 feet, the Jin Mao Tower is one of Shanghai's most enduring symbols of modern China. It was completed in 1999, in the heart of the city's Pudong district. It was built on a site that's both geologically challenging and seismically active. It sits near the Yangtze River Delta, where the soft soil and the influence of tectonic movements from the Pacific Rim combine to create some complex seismic risk. The tower was built to withstand earthquakes up to magnitude 7.0. The engineers faced two main challenges: the city's unstable soil and the potential for strong lateral shaking. To address this, they employed an intricate system of deep foundations, flexible steel framing, and energy-absorbing joints. The building is sitting on over 1,000 concrete and steel piles that extend as deep as 83 meters into the ground, anchoring it into the dense layers of clay and sand below the city. Above the foundation, the main frame is composed of a steel lattice encased in reinforced concrete, forming a composite system that blends strength and flexibility. It's modeled loosely after a traditional Chinese pagoda. The building narrows as it rises, reducing the wind and seismic load at higher levels. Each of the 16 tiers is proportionally scaled by 1/8, creating visual harmony. The tower's exterior is supported by a truss system that acts like a flexible exoskeleton. The building can safely sway up to 75 centimeters at the top without compromising any integrity, a movement that would barely be noticeable to the occupants. During several moderate quakes over the past 2 decades, including those originating in nearby provinces, the tower's internal sensors recorded minor vibrations, all well within safety limits, and no structural damage has ever been reported. And of course, it incorporates redundancy in its safety systems, ensuring that even if some structural elements were compromised during a major event, others would continue to carry the load. Though newer and taller skyscrapers have since joined the Shanghai skyline, Jin Mao is still a benchmark for how to build securely. Number 6. The Torre Costanera, Chile. Torre Costanera. It's officially known as the Gran Torre Santiago. It's the tallest building in South America, and it stands in one of the most earthquake-prone countries on Earth. It stands about 984 feet, that's 300 meters above the Chilean capital. The tower was designed from the ground up to endure the seismic forces generated along the boundary between the Nazca and the South American tectonic plates. In Chile, earthquakes exceeding magnitude 8 are not just possible, they're expected. Construction of it began in 2006 and was completed in 2014, with design work led by architect Cesar Pelli and structural engineering by the Chilean firm René Lagos Engineers. The guiding principle of the project was simple. The building has to survive the largest conceivable earthquake without collapse or permanent structural damage. To meet that goal, engineers had to combine Chile's rigorous seismic codes with some of the most advanced damping and structural reinforcement systems in the world. The structural core is made of reinforced concrete more than 2 meters thick, which houses the elevators, stairwells, and utilities. Around this central spine, a network of high-strength steel beams and concrete columns forms a flexible outer frame. This system does allow for controlled movement during ground shaking, which enables the tower to sway without cracking. Engineers designed the structure to remain fully elastic during quakes as strong as magnitude 9.0, which is an unprecedented standard for South American high-rises. At its foundation, it rests on 56 reinforced concrete piles that extend about 50 meters down into stable gravel layers beneath Santiago. This design underwent extensive computer modeling and scale testing at the University of Chile's Seismic Simulation Laboratory. These studies replicated the ground motion patterns of Chile's most destructive quakes, including the 1985 Valparaiso quake and the catastrophic 2010 Mole earthquake, magnitude 8.8. Torre Costanera was still under construction when the 2010 event struck, but the partially built structure sustained no damage, which was an early validation of its design. But beyond the technical achievements, it symbolizes Chile's adaptation to living with quakes. In a region where seismic activity defines daily life, this skyscraper shows that preparation and precision can turn vulnerability into stability. Number 5. The U.S. Bank Tower. The U.S. Bank Tower, formerly known as the Library Tower, is one of the most prominent features of the Los Angeles skyline. Completed in 1989 and standing 310 meters or over 1,000 feet with 73 stories. It was designed to withstand the powerful ground motions generated by the nearby San Andreas and Puente Hill faults, both capable of producing magnitude 7+ quakes. The design had to balance its height, flexibility, and safety all within one of the world's most active seismic zones. The foundation extends about 27 meters down, 90 feet into the ground, anchored by deep concrete piles that penetrate into layers of sand and clay below downtown LA. Its core consists of a robust concrete shear wall system surrounded by a perimeter of moment-resisting steel frames. Now, these steel frames are engineered to flex during a quake, which absorb the energy and reduce the stress on the concrete core. Because of the height and slenderness, though, wind was a significant factor in its design. Engineers had to use wind tunnel tests and computer models to ensure that both wind and quake loads would not cause excessive sway or discomfort. When the 1994 Northridge quake, magnitude 6.7, struck just a few years after the tower's completion, it served as an early test. Although the epicenter was about 30 kilometers away, downtown LA experienced strong shaking. The U.S. Bank Tower emerged completely undamaged. Detailed inspections afterwards confirmed that all structural components performed exactly as intended. More recently, engineers have retrofitted parts of the building to meet updated California seismic codes introduced after the year 2000. The modernization included additional damping systems and a structural health monitoring network that uses accelerometers to record any vibrations during small tremors. This data helps engineers continually refine models for how tall buildings respond to different frequencies of ground motion in Southern California. Even after newer skyscrapers like the Wilshire Grand surpassed its height, it remains one of the safest and best-studied towers in California. Number 4. The Gakuen Cocoon Tower in Japan. Tokyo's Gakuen Cocoon Tower. It is a marvel as much as it is an architectural statement. Completed in 2008, this 204-meter or 669-foot skyscraper in the Shinjuku district has 3 educational institutions within it. But beneath its futuristic facade is a structure that's meticulously designed to survive Tokyo's frequent earthquakes. Given its location in one of the world's most active seismic regions, the design team employed advanced structural systems that merge the aesthetics with strength, ensuring that the building can flex and absorb energy rather than resist it rigidly. The exterior Cocoon design isn't merely decorative, it serves as a diagonal bracing system that reinforces the structure against lateral and vertical movement, and this reduces the strain on any single part of the building during a quake, allowing it to move uniformly and prevent localized damage. The core consists of reinforced concrete and shear walls that provide vertical and torsional stiffness, and those walls are connected to the outer shell by large horizontal beams at each floor. Engineers designed the frame with ductile steel joints that are capable of yielding without cracking. That's a feature that allows the tower to survive large earthquakes with only minimal damage. The entire building can sway several centimeters during strong quakes, but the motion is carefully controlled to prevent any damage to the internal systems and discomfort to its occupants. Tokyo's building codes, among the world's most demanding, require skyscrapers to withstand severe shaking without collapsing. The Cocoon Tower exceeds all the standards. During multiple moderate quakes since its completion, including the 2011 Tohoku quake, the building performed exceptionally well. By eliminating any sharp corners, the design does reduce the concentration of stress at any key joints. It's a critical advantage during quakes. The curved facade helps distribute lateral pressure smoothly, which is an approach that's inspired by traditional Japanese wooden pagodas. Inside, the building's open atriums and vertical shafts were engineered to accommodate slight movement between the floors, ensuring that internal walls and fixtures don't crack or detach during tremors. In a city where seismic safety is non-negotiable, it does prove that strength will coexist with elegance, a building that quite literally bends, but will not break. Number 3. The Torre Reforma, Mexico. Standing 807 feet tall, that's 246 meters in Mexico City, Torre Reforma is one of the most earthquake-resistant skyscrapers ever built. Completed in 2016, this 57-story tower stands directly on some of the most unstable soil in the world for high-rise construction. In a city regularly shaken by powerful quakes, including the deadly 1985 and 2017 quakes, Torre Reforma's design had to do more than meet code. It had to redefine what was possible. The building's structural system is unconventional but ingenious. Instead of a typical rectangular core, it uses two massive triangular concrete walls known as shear walls that rise along the sides like open bookends. Between them, a lighter steel and concrete frame allows for movement and flexibility. This configuration channels the seismic energy along the two giant walls, which act as stabilizers, while the central section moves independently, dissipating energy rather than transferring it. The structure features the large, deep-set windows and seismic joints between any major components. Those gaps allow parts of the tower to shift slightly without breaking. And at its foundation, the engineers had to install a mat slab nearly 5 meters thick, and they anchored it with deep piles that extended to firmer soil, layers below the lakebed sediment. This tower's design was immediately tested. When the 7.1 magnitude Puebla earthquake struck in 2017, just a year after completion, the tower swayed visibly, but it sustained no structural damage. Nearby buildings suffered cracked facades and fallen glass, but this one remained fully functional. During the 2017 quake, sensors recorded ground accelerations higher than those used in its design simulations, yet the structure performed exactly as predicted. That event alone validated years of research into this flexible, energy-dissipating design. Torre Reforma is one of the greenest tall buildings in the Americas. It holds LEED Platinum certification, but its best achievement is its durability. Even after experiencing one of the most destructive quakes in Mexico's modern history, it needed no structural repairs. It doesn't just resist earthquakes, it flows with them, bending gracefully as the ground moves beneath it. It's a rare example of architecture and engineering that merges into a single unified response to nature. Number 2. The Mori Tower in Japan. Located in Tokyo's upscale Roppongi Hills district, the Mori Tower stands 781 feet, that's 238 meters. It's one of Japan's most thoroughly engineered skyscrapers for seismic safety. Completed in 2003, this 54-story tower is a centerpiece of one of Tokyo's largest urban redevelopment projects. Given Tokyo's location near multiple fault lines, including the Sagami and Nankai troughs, it was designed to withstand some of the most severe ground motion. The building's main frame is a composite system of reinforced concrete and high-tensile steel. A central reinforced core has the elevators, utilities, and stairwells, surrounded by a network of steel braces that act as shock absorbers. The perimeter columns are linked to the core by outrigger trusses at several mechanical floors, which distributes the lateral loads evenly across the structure. The foundations are anchored deep into the ground, roughly 60 meters below ground. Base isolators, large rubber and steel bearings, separate the structure from the ground itself, allowing the building to sort of float slightly during a quake. This base isolation system reduces seismic force by up to 80%, which ensures that most of the ground motion never reaches the tower's upper levels. One cool feature of this tower is the network of oil dampers installed between the floors. These are hydraulic devices that absorb vibrational energy much like the suspension system in a car, converting the motion into heat and reducing the sway. The dampers are tuned to respond to different frequencies of vibration, providing protection from both short and sharp jolts or long-period oscillations that can affect tall buildings. When the 2011 Tohoku quake struck, one of the strongest ever recorded, Tokyo experienced prolonged shaking. The Mori Tower performed exceptionally well. Elevators automatically stopped as designed and emergency systems engaged without failure. Within hours, the building was cleared for re-entry. Today, Mori Tower is a benchmark for urban earthquake design in Japan. It shows how the latest materials, the base isolation, and that dampening system can combine to protect human life and infrastructure. In a city where the next major quake is not a question of if, but when, the Mori Tower stands as a reminder that thoughtful engineering can make even the tallest structures move in harmony with the planet. Number 1. Shanghai Tower, China. At 632 meters, or 2,073 feet, the Shanghai Tower is the tallest building in China and the second tallest in the world, and it stands on ground that has enormous seismic challenges. Shanghai sits on deep, soft clay deposits in the Yangtze River Delta, which is an area that's susceptible to strong typhoon wind and moderate but potentially damaging quakes. Constructing a megatall skyscraper on this kind of soil required one of the most sophisticated foundation and damping systems ever designed. Completed in 2015 after nearly 7 years of construction, the tower was designed by Gensler and engineered by Thornton Tomasetti in collaboration with the Shanghai Research Institute of Building Sciences. From the outset, the engineers understood that while Shanghai is not seismically active as Tokyo or Santiago, a combination of soft soil and regional seismicity made earthquake resistance just as crucial as wind resistance. The foundation extends 86 meters deep. It's one of the deepest in any skyscraper, with 947 reinforced concrete piles. It sits above a 6-meter-thick concrete mat weighing more than 120,000 tons. This enormous base spreads the building's weight evenly, and it prevents any differential settlement. The structure uses a reinforced concrete core surrounded by a steel frame megatube. This dual system gives the building exceptional lateral stiffness while allowing a controlled flexibility. At 9 mechanical floors spaced along its height, a series of outrigger trusses link the core to the outer columns. These trusses support a massive damping system, which is a 1,000-ton tuned mass damper mounted near the top that counteracts the sway during both windstorms and quakes. Wind tunnel and seismic testing confirmed that the Shanghai Tower could safely withstand quakes up to magnitude 7.0, as well as typhoon winds exceeding 50 meters per second. During a moderate quake in 2012, while the building was still under construction, sensors recorded movement consistent with predictions and no structural distress, an early real-world validation of this design. Because of the twisting shape, though, which rotates about 120 degrees from base to crown, the tower naturally disperses lateral loads. That kind of geometry reduces wind drag by nearly 25%. The facade's double-layered curtain wall, meanwhile, provides extra stiffness and insulation without adding any excessive weight. Even though Shanghai's quakes are infrequent compared with Japan's, the city's soil conditions make every tremor potentially destructive. This tower's engineering does prove that durability depends on not how often the ground moves, but on how well a structure is prepared when it does. This tower is a vertical demonstration of how human design can coexist with the unstable Earth. Rising gracefully above a region once thought unsuitable for this kind of height, it shows that with careful engineering and respect for the forces of nature, even a megatall tower can move in harmony with the planet and stand secure against its tremors.